Piecewise linear constraints allow the user to define a decision variable as a piecewise linear function of another variable. These functions are particularly useful to model stepwise functions or approximate nonlinear functions. Consider the example where discounts apply depending on the quantity of items bought, up to a maximum of 200 items. 4 breakpoints x, which are associated with the buckets defined for the discounts, exist where the price function changes. The total cost y at a given breakpoint x can be calculated using the x and y values of the previous breakpoint, following the formula on the slide. Such piecewise linear functions can be conveniently added to a problem via the xp.pwl method. The method receives a dictionary as argument. The keys of the dictionary should contain a tuple of 2 elements, which specify the range of the input variable for which an expression, specified in the value fields of the dictionary, should apply. Modeling the previous discount example, the express.pwl method is used to model the cost function by passing it a dictionary with the intended intervals as keys, and the calculated function expression as values. The cost variable y is then constrained to be at least the value of the piecewise linear function via the p.add_constraint method. You can also use xp.pwl when defining constraint expressions and objects, such as in the quadratic constraint example shown, where the values of the y and z variables are constrained to follow a piecewise linear function of variable x. The PWL method can be particularly useful to model step functions. In case a variable does not appear in any of the values, an extra key value pair must be specified with none as key, and an arbitrary decision variable of the model as value. The method also works if a function y is not continuous along the domain of x. See the Optimizer reference manual for more information about the special cases when modeling such piecewise linear functions. The Python notebook example named piecewise_linear shows how to create a simple problem using the modeling constructs problem.add, PWL cons, and express.pwl. In this example, a piecewise linear function is created to approximate the trigonometric function sine of 5x using a predefined number of breakpoints. First, we define a function, named createSegments, which returns the breakpoints x and their corresponding y values as lists for a specified number of breakpoints and frequency value. In a first modeling approach, the problem.add PWL cons function is used for creating and directly adding piecewise linear constraints to a problem by passing the coordinates of each breakpoint. The breakpoints and corresponding values, computed using the previously defined function createSegments, are passed as arguments after the decision variables x and pw. The latter variable is set as the output variable of the piecewise linear function, and is also set as the objective to be maximized. By running the cell for n equal to 10 breakpoints, we can observe in the plot in output pane the original nonlinear function, as well as the piecewise linear function used for approximating the original function in the optimization problem, with the corresponding optimal solution plotted as a green dot. In the second part, the method express.pwl is used, which returns a piecewise linear function in variable x, specified via a Python dictionary that contains as keys the intervals, and as values the corresponding linear expressions in a variable. For stating these expressions, the slopes of the linear segments are required along with the breakpoints and function values. The objective is set to maximize the value of the piecewise linear function. By running the code cell for the same number of breakpoints, we verify that the same approximation and final solution are obtained. As an optional exercise, you can increase the number of segments and iteratively to decrease the gap between the piecewise linear and the original nonlinear functions.